At the instant shown, the three particles are at the corners of an equilateral triangle, with particle 1 chasing particle 2, particle 2 chasing particle 3, and particle 3 chasing particle 1. They all have equal speeds. Watch what happens when they start chasing. They meet at the center of the equilateral triangle, and the paths followed are a little complicated, but one thing you should be able to notice is as they get closer to each other, the velocity vectors rotate very rapidly. Watch if I've just shown the path of one of the particles, and it's a curved path with tangent. You can see the tangent of the path which represents velocity turning very sharply as the particle approaches the center of the triangle. You could have had more particles, like say 6 of them chasing. You can notice the hexagon rotating very quickly, very rapidly when the size becomes smaller. Watch again. Three particles are at the corners of an equilateral triangle, and the velocities of the particles are directed as shown. Say velocity of 1 is directed at the position of 2, velocity of 2 is directed at the position of 3, and velocity of 3 is directed at the position of 1. At the initial moment, they form in the line joining their positions forms an equilateral triangle. They all have equal speeds. So our interest is to find when they meet. We know where they meet without having to calculate. They meet at the center. There is symmetry. As you can see, the triangle shrinks in size and rotates, and the particles are going to meet at the center. We would like to find how long it takes to meet at the center. That's the only calculation we can do easily. It's a two-dimensional motion. A typical analysis would be to set up an x-axis, y-axis, split velocities into components. But this is much too complicated for that. But as far as time is concerned, it's really nice and simple. What you do see is that at any moment the particles would be at the corners of an equilateral triangle. The particle here would have moved somewhere to this position, say something like this would have happened, right? They would have moved along a curved path, and the line joining these would be again another equilateral triangle of a shorter size. That is, the triangle would rotate and shrink in size. Now at any arbitrary moment we could look at something like this, the side of the triangle, the side of the triangle. If the initial length, the initial distance, initial side is L, you see that due to motion of 1, the velocity of the line joining the 2 of 1 and 2 decreases at the rate v, and due to this the velocity v at an angle of 60 degrees, this is after an equilateral triangle, the component is v cos 60, that is v by 2 towards 1. So velocity component 2 towards 1 would be, along the line would be v by 2, v cos 60, v by 2. So that line is shrinking at the rate of v plus v by 2. This end is moving at 1 v, and this end is moving towards 1 at v by 2. That's 3v by 2. So when they meet, the length of the line would be 0. So what is the time when they meet? Length of the line by 3v by 2, that is 2l by 3v. Interesting, simple solution. Another thing that you could do is consider the line joining the center of the triangle to the position of any particle. This line rotates and shrinks. If you know the initial length of the line and the velocity component along the line, this would be 30 degree, right? Velocity component along that line, you would be able to get the time when the particle 2 reaches the center. So what are we going to look at? Line joining the center to, that's where they're going to meet, to the position of the particle, say 2. And the velocity of 2 along this line is v cos 30, root 3v by 2. All you need to know is the length of this line. That's known, right? The length of the line initially, the side of the triangle, the length. For example, this would be, this is L by 2, this is L by 2, right? And this angle is 30. So L by 2, cos 30 would be this length by this. So we know this L by 2 by cos 30. So L by 2 by cos 30 degree divided by, that's the length of that line. This component is v cos 30. So this is the time. L by 2v cos squared 30. Cos 30 is root 3 by 2. So 3v 3 by root 3 by 2 whole squared. So this is 4 here. So that is 2L by 3v. Well, interesting. That is, the line is rotating and shrinking in size, and you would like to find the time when they meet. It could be any number of particles. You could have 6 particles at the corners of hexagon, or 4 particles at the corners of a square. We can solve for the time this way. If it is 4 particles at the corners of a square, then again, if you are looking at say the same condition, like velocities are like this. Velocity of 1 is aimed at position of 2, velocity of 2 is aimed at position of 3, and 3 is at 4, 4 towards 1. It's at all moments. So this square will shrink in size and rotate. And if you look at the line joining 1 and 2, initial length, say, is L again. Initial side of the square is L, say. So this is L. The velocity component of 2 along the line is 0. So the velocity along the line 1, 2, the line 1, 2 is shrinking, right? That's v. So that's the L by v. So this t is L by v. Or of course you can look at the line joining the center of, that's where they're going to meet, square. This will be L by root 2, and this velocity component will be v cos 45, that's v by root 2. So that will be L by root 2, length of this line initially, and velocity component is v by root 2. So that's nice. There is a reference line here whose behavior is simple. In spite of all the complicated nature of the motion, there is something simple to look at. So, well, for a moment we should go away from our regular routine thinking, where we would think of any two-dimensional motion in terms of x-axis, y-axis, splitting velocities into components and writing equations. It is a complicated motion with variable acceleration, but there is one thing simple that you can solve.